introduction, I was attending the Scholar One conference. I think it was just called Scholar, not Scholar One, like 10 years ago. And it's a great pleasure for me to attend this conference as a speaker this time, okay? So thanks everyone for being here. All right, so what is this? Let me tell you a little bit about how I met Professor Murty by the first time. I was a student at Queen's. I arrived in 2011 to study under Murty. And yeah, so I arrived late, 2 weeks late actually, to the beginning of the semester. Oh, what's this?
1 second, sorry. It was not sharing properly?
Okay, okay, sure. No problem.
It should be showing now. Yeah, you're good.
It's good? All right, thank you. Good, so I arrived late. Good. So my first day on campus was a Friday. I remember this like if it were yesterday. And I went to the colloquium talk. I was sitting near the exit of the room, and I didn't talk to anyone because I was afraid of people. I mean, I was very shy by then. And I didn't talk to Professor Murty at that time. And after some time, maybe it was 2 weeks or a week later, I talked to Professor Murty. We were not having regular meetings. Everyone else was having regular meetings, the postdocs, the other students. And I felt guilty for this because I arrived late. I didn't talk to him, so there's no way he could know that I was around. All right, so yeah, so one day I asked for a meeting, and we had this meeting, and he gave me a bunch of papers. All right, so I sorted the papers by topic, and I ended up with 2 piles. One was on GRH, and the other on ABC, and I was supposed to choose a thesis topic out of this. So I went for the easy one. All right, so when I was a kid, I read about the ABC conjecture in this elementary number theory book of Nathaniel, and I liked the exposition, I liked the problem. It was very elementary, so it was easy to understand, not like GRH, and I was just starting my PhD. And here's the conjecture. The conjecture, well, we already saw the radical in the previous talk. The radical is just the largest square-free divisor of an integer. And the conjecture is that if you have an additive relation, a plus b equals c, between coprime positive integers, then the largest of the integers is bounded by a power of the radical. And this is quite interesting because you can have, for instance, a large power of 2, and the radical is quite small, it's just 2. However, this cannot happen if you have an addition in the middle, okay? If you add integers, somehow the multiplicative structure knows about this addition, and the radical is going to be large. And there is even a stronger version of the conjecture saying that the exponent can be taken as 1 plus epsilon, up to finally many exceptions. All right. But I think we all have seen this conjecture before. Consequences, there are plenty of consequences, and there is plenty of people that can tell you about these consequences in a better way than what I can do, so I will not talk about consequences, okay? So I want to talk about how to attack the question and conditional approaches to the ABC conjecture. Of course, it's not going to be proved today, and it's an open problem, at least outside of Japan. And all right, so the papers that Professor Murty gave me, they have a lot of ideas about how to attack this question, and I want to tell you a little bit about this. But for that, I need to review some classical stuff, because the ABC conjecture, you see, the main difficulty is similar to the main difficulty of Fermat's last theorem. The question is so elementary that you have no idea how to put heavy machinery into the question. So it's not easy to relate the question to deeper ideas in number theory. It's just too elementary when you read the statement. So the first connection with more advanced number theory is via elliptic curves. And so when you have an elliptic curve, there are a few invariants attached to the elliptic curve. One of them is the minimal discriminant, and another one is the conductor. And as we all know, the conductor divides the minimal discriminant. So you have a trivial inequality, well, trivial, coming from the divisibility, which is the conductor is less than or equal to the discriminant. And there is a conjecture by Spiro that says that there is an inequality the other way around, okay? That the discriminant is bounded by a power of the conductor. And in fact, this conjecture was stated before the ABC conjecture, and the ABC conjecture was an attempt to extract something, some elementary statement out of this conjecture. So how's the connection? Well, if you take A, B, and C positive coprime integers having A plus B equal to C, then you can write down this particular elliptic curve, and after a little computation, you realize that the minimal discriminant is A times B times C squared, and the radical is actually equal to the conductor, up to some bounded power of 2. I didn't bother writing down, but essentially this is correct. So when you look at the conjecture by Spiro, you will see that the minimal discriminant is measuring the size of the variables, okay? And the conductor is the radical. So when you have the inequality, delta less than or equal to n to the power k, you end up with a version of the ABC conjecture. So one approach is by means of elliptic curves, okay? So Spiro implies ABC. Another approach is by means of the height conjecture, and there is a notion of height of elliptic curves. This is the Faltin's height. It's defined using Arakelov geometry. And the conjecture is that the height of the elliptic curve, which is logarithmic, is a logarithmic height, is bounded by a multiple of the logarithm of the conductor. Okay, so that's a conjecture. I'm not reviewing here what's the Faltin's height, but just let me tell you that it has the basic properties you would expect from a height. So the Northcote property, for instance, if you bound the height, you end up with finally many isomorphism classes of elliptic curves over Q. And well, one can show, it's not too difficult to show using the actual definition of this height in terms of Arakelov geometry. You can show that it's bounded from below by a multiple of the logarithm of the minimal discriminant. So in this way, you see immediately that the height conjecture implies Spiro's conjecture, and therefore it implies the ABC conjecture. So now, okay, fine, now we can use Faltin's heights to attack the ABC conjecture. And there is another approach by means of the modular degree conjecture. Today we know that elliptic curves over Q are modular, and there are many manifestations of this modularity. One is by means of modular forms, another one is by means of Galois representations or L functions, but there is also the geometric modularity, which says that you have a non-constant map coming from a modular curve to the elliptic curve. Now, something interesting is this n. I don't think the pointer is working. Okay, it's not working, but x0n, when you see this n, is actually the conductor of the elliptic curve, okay? Is the conductor. So I think this is quite important because you can now read the radical on the modular side. So the modular degree conjecture is that the logarithm of the degree of this map, if you take the degree to be minimal, okay? Okay, I didn't write down properly the phi. The first one is bar phi, the second one is regular phi, but it's the same phi, okay? So it's saying that the degree of this map, if it's chosen minimal, is bounded by a power of the conductor, okay? And now this looks more reasonable because this map is coming from modular forms, and the conductor is also coming from modular forms. So it's not so crazy to have a relationship between these two. And well, a simple computation shows that the modular degree can be used to bound the Faltin's height. And therefore, the modular degree conjecture implies the height conjecture, which implies the Spiro conjecture, and then it implies the ABC conjecture. So now we can use modular forms to attack the ABC conjecture. All right, so some contributions by Professor Murty. Of course, he did way more than this, but I'm just pointing some contributions that are related to the discussion we had before. So actually, the height conjecture is equivalent to the modular degree conjecture. Okay, that's a first contribution. I'm not following chronological order. It just I just want to mention some contributions. There is also the relationship between the ABC conjecture and Chafarevich-Tate groups of elliptic curves, and this was joint work by Professor Murty and May. But this was also independently discovered by Goldfeld and Spiro. There is also some unconditional bounds for congruence primes. And this is interesting. You can put your hands on congruences of modular forms by means of Hecke operators. or coefficients of modular forms. And that's useful because there is a theorem of Rivet that says that the modular degree divides a number that measures congruences. So if you can bound the congruences of modular forms, then you can bound the modular degree, and then you can bound everything else. And Professor Murty got some unconditional bounds for congruence primes. And he also introduced, and I think this is important because I don't think people have looked at this so deeply. Professor Murty and Lee, they introduced Dirichlet series in the study of the ABC conjecture. And I think this deserves more attention. Okay, so the approach to the modular degree conjecture by Professor Murty is that if you have an elliptic curve, as I mentioned before, there is this theorem of Rivet that says that the modular degree divides the congruence number, and the congruence number is measuring congruences of the modular form attached to the elliptic curve. So this modular form, if you normalize it as a new form, the Fourier coefficients are integers. So it makes sense to talk about congruences, coefficient by coefficient. Okay? And it measures congruences with other modular forms. I don't want to be too precise here. It's not the point of the talk. And Professor Murty introduced a method to bound this using matrices built out of coefficients of modular forms. And then you get unconditional bounds, which are exponential. So the logarithm, there is no typo here. The logarithm of the degree is bounded by a power of the conductor. You want a multiple of the logarithm of the conductor. So this is exponential, but nonetheless, it is unconditional. Okay, that's the point. It's an unconditional bound. And therefore, you get exponential bounds for the ABC conjecture. But I'm going to get to that point. Okay, there are better ways to get exponential bounds for the ABC conjecture. All right, so in our joint paper, the first joint paper we had, modular forms and effective Diophantine approximation, we revisit this approach by congruences of modular forms, but from a more abstract point of view. Instead of looking at matrices built of coefficients, we use the discriminant of the Hecke algebra, okay? So we look at this more abstractly, and as a result, we get a better bound. And the bound is that the modular degree in logarithm is less than or equal to 1/5 n times log n. And this is completely explicit, okay? And from this, you keep track of everything else I said, and you get some completely explicit bound for the ABC conjecture, which is exponential. However, all constants are completely explicit. You can write them down, and they are not too big. And since they are not too big, you can use modularity of elliptic curves to compute solutions of certain Diophantine problems, like the S-unit equation. And I think this was the first time the modular approach was used, to get your hands on classical Diophantine problems and to do the computations, actually. Like you set a set of primes, like 2, 3, and 5, and you want to compute all the solutions of this S-unit equation. Now you can do it explicitly thanks to the, well, it's not the first time you can do it, but it's the first time you can do it using modular forms. And this was followed up by work by other people later. All right, so fine, very nice. We have modular approach to the ABC conjecture. You get exponential bounds for the ABC conjecture out of modular forms. However, here's the first advice that Professor Murty gave me. Not the first during my PhD, but the first I want to mention here. Read Stuart Tiedemann and Stuart Yu. Okay, read that. So what is this? They had a different approach using linear forms in logarithms, and you get better results. So let me go quickly to the last one. The last one says that you have an exponential bound for the ABC conjecture with the exponent of the radical being 1/3. This is beyond what you can get with modular forms, okay? With modular forms, you will get exponent 1 plus epsilon, not 1/3 plus epsilon. So as far as ABC is concerned, the Stuart Yu approach remains today as the strongest one. However, if you look at the Spiro conjecture, the height conjecture, the modular degree conjecture, this approach will not work, okay? Not in general for all elliptic curves. And still today, the strongest bound that remains is the one we proved with Professor Murty. So it's a very challenging problem trying to get a power saving in this bound, to go below exponent 1. All right, so the other advice he gave me to attack the ABC conjecture is to look for radicals in the wild, okay? So you go hunting radicals out there. And linear forms in logarithms are useful because the radical appears after you apply the geometric arithmetic inequality. So the radical will show up naturally in the linear forms in logarithm bound. Elliptic curves, as I mentioned before, are useful for ABC because the conductor is essentially a radical. So this is another instance where the radical naturally appears. And modular forms are useful because the level equals the conductor of the elliptic curve. So again, you can read the radical in a naturally occurring way. So Professor Murty encouraged me to look for radicals in other situations that naturally occur in mathematics. And I had an idea, quaternion algebras, the discriminant of quaternion algebras. I don't think I ever told him, but at that time I wasn't completely familiar with quaternion algebras. I just knew the basics. And I thought, okay, the discriminant of a quaternion algebra is also square-free, and it's also radical. And I thought not so deeply about this, and it didn't work. I didn't get anywhere with this idea. Okay. So, and the last piece of advice I want to mention is to mix modular forms with the linear forms in logarithms. You have these two approaches that look a little bit like orthogonal, because modular forms is more in the representation theory or arithmetic geometry side, and linear forms in logarithms is more analytic and transcendental number theory. So how to mix these two? So two people insisted on this. Professor Murty, during my thesis, he encouraged me to mix these two approaches, and I failed, okay? It didn't work. And then my wife, she told me, I mean, every time I complained to my wife, I failed to prove ABC again. I tried for months with this new approach and it didn't work. She will tell me, okay, but have you tried to mix linear forms in logarithms with the modular forms? No, I haven't, but this time I followed that advice, okay, because I took this more seriously. I mean, one thing is your supervisor tells you to do something, but a different story is when your wife tells you to do something. But it didn't work either. Okay, so what's the problem? The problem is that when you want to mix the two approaches, you end up on the common ground, and the common ground is Frey curves, okay? So elliptic curves that come from ABC triples. That's the common ground, okay? But for these elliptic curves, linear forms in logarithms already give you a better result. So there is no room for mixing with the modular approach in this common setting. So at least today, I see that this is the reason why my attempts failed. So what I really needed here is something truly new, something that gives you information that's not covered by the modular approach and is not covered by linear forms in logarithms, and then maybe you can mix this with the two of them. So I graduated in 2014, and after that I went to Harvard, and then during this period I spent a year at the IIS. And one day in fall of 2015, I was in my office at the IIS, very frustrated because I had to write a grant proposal. Right, so the last part was the bibliography, and that was quite annoying because you have to search the bibliography and you need to make sure that everyone that could possibly be a reviewer is cited. And okay, so reading the bibliography, I came across a paper that somehow escaped my attention during the PhD. It was this paper by Rivet and Takahashi. And the paper says a formula, and the formula is that the modular degree divided by a Shimura degree, I will mention what this is equal to the product of the exponents of the minimal discriminant. There are some technicalities here. You need to choose an auxiliary capital D and so forth, but essentially that's what it says. So what is this degree on the bottom of the fraction? It's like the modular degree, but instead of using a modular curve, you use a Shimura curve. And the Jacob-Langlands transfer tells you that the existence of a modular parametrization implies the existence of the Shimura curve parametrization. So you have these two degrees, you look at the comparison of them, and you end up with the product of the exponents of the minimal discriminant. And if you know Professor Murty, you will know that, well, he focused his research on many aspects, but two aspects that show up quite often are averages and error terms, okay? And usually it occurs quite often that the key to attack a problem is either looking at averages or trying to improve the error terms. And in this case, what I see here is an average, a multiplicative average of the exponents of the minimal discriminant. So it looks like a very interesting quantity. And I wanted to put my hands on this. So according to this formula, I should look at the comparison between these 2 degrees. The problem is that this formula is not so clean. It had plenty of conditions, and all of these conditions failed in the case I cared about. Okay, so for instance, for Frey curves. For Frey curves, you cannot apply this theorem. So I spent a few months working on this, and eventually it worked. Okay, so after a few months working on trying to get rid of the conditions, I could do it, not in the form of this clean formula, but with some additional error term. But Professor Murty told me many times you need to control error terms, you need to bound error terms, and I bounded the error term in this formula. And fine, so I had the formula. And then I had to do something with the formula. And the idea was to control the product of the exponents of the minimal discriminant, so I had to focus on the comparison of the 2 degrees. And well, after 2 years, it worked, okay? After 2 years, I was able to bound this comparison. And that was kind of a lot of work. It used analytic number theory and hyperbolic geometry and modular forms and Galois representations and arithmetic geometry, integral models, and so forth. It was really painful, but eventually it worked. And the theorem is this. You take a finite set of primes. You can ignore this and think about semi-stable elliptic curves. This is just a technicality to make the theorem more flexible, okay? So if you have an elliptic curve, which is semi-stable, the product of the exponents of the minimal discriminant is bounded by a power of the conductor, okay? And this does not follow from linear forms in logarithms, and it does not follow from the classical modular approach. It's something truly new. It's a different story. And for ABC, I got a similar statement with a better exponent, 8/3. And this is the output of this new approach to ABC by means of Shimura curves. So why is this something you should think about? Well, it's something new, okay? It's different. So you have a chance to mix it with the other approaches. And it helps to control large exponents on an ABC triple because it is a corollary that when you have an ABC triple, you look at the exponents. How many exponents go beyond a bound B? Well, this many at most. Logarithm of the radical divided by logarithm of the bound. Okay? Just because you have this multiplicative average. When you have a bound for an average, you get a bound for how many large terms you have in your average. That's one reason why we care about averages. So just for comparison, the trivial bound for the number of divisors, for the number of primes dividing ABC is logarithm of the radical divided by log of the radical. So in principle, you can take capital B larger than log of the radical and get a better estimate for the number of large exponents in the minimal discriminant. And so we have these 3 unconditional approaches. I'm almost done. One is the linear forms in logarithms. The other one is the classical modular approach. And now we have this new one, with Shimura curves. And now one can combine the 3 of them, okay? This is not something I realized immediately. This is something I realized last year in November. So how is this? So linear forms in logarithms give you a bound of this sort when you have a product of logarithms of certain integers, okay? So if you want to get a better bound, you need this product to be short, to have very few terms. So if you don't have more information, these integers are going to be, these psi j's are going to be the prime divisors of ABC, okay? However, using what I mentioned before, the only terms that you really care about are the prime divisors with large exponents, and you have very few of them using the Shimura curve approach. So you can improve drastically this linear form in logarithms bound. And some applications require elliptic curves, not linear, not the ABC triples. So for elliptic curves, you in addition need to apply the classical modular approach to bound individual exponents that are somehow not covered by this computation. Okay. So yeah, for elliptic curves, if you want to get an improvement on what we know, you end up using the 3 approaches altogether. So here's an application. Script P is going to be the largest prime factor, And one can show this bound, that the largest prime factor of n squared plus 1 is bounded from below by the square of the log n, with this denominator which is not growing too fast. Okay? And for the sake of comparison, what we knew before was essentially the square root of that. There was an improvement in the 2000s using linear forms and logarithms after an idea of Stewart and Yu, but still that improvement, the main part of the bound still is log n. And now we have something that's like the square of that. And after 90 years. So in recent work with one of my master students, we generalized this for every quadratic polynomial, which is not a square, of course, okay? Using algebraic number theory and more clever constructions of elliptic curves that he came up with. So for this theorem, the elliptic curve you need to think about is this one. But for quadratic polynomials in more generality, you need to write down something more complicated. And for ABC, we get this bound, which the only thing I want to mention is that this is sub-exponential. But you have to pay a price, and the price is that it's not for all ABC triples. It's for ABC triples where one of the variables is somehow smaller than the other one. Okay, I'm almost done. So I have time? Yeah. Okay, good. So, oh really? Oh, excellent, good. So I have time to mention this. Good. So the condition is that A has a power saving compared to C. Okay. Now imagine you can prove the ABC conjecture in this setting. It's not so restrictive because there are plenty of problems where A is just a constant, like the Catalan equation, for instance. In the Catalan equation, you have a power plus 1 equals a power. Okay. So that's an example of an ABC problem where one of the variables is quite small. Okay, so if you could prove the ABC conjecture under this additional assumption, that would still be good. So I thought maybe it's worth attacking this question under this additional assumption, and one can get a sub-exponential bound with this term, which is square root of logarithm of the radical inside the exponential. Right, and I got a similar estimate where you no longer assume the condition that one of the variables is small, but instead the bound will include in front of the exponential. In front of the exponential, you will have a term factor q, where q is measured in terms of the prime factors of ABC. And such a bound is not new. This sort of bounds coming from linear forms in p-adic logarithms is already included in the work of Stewart and Yu. The new part of this bound that I obtained is that although the shape is similar, what goes inside the exponential is considerably smaller. Okay, so you get an improvement on the bound, and this is obtained by mixing the three approaches: the modular approach, the Shimura curve approach, and linear forms in logarithms. By putting all together, you get these improvements on bounds for the ABC conjecture. All right, so yeah, so what about ABC more variables? To my knowledge, we know nothing, okay, unconditionally. There are analogs for polynomials and function fields in more generality, and we know the relationship with conjectures of Boita, but if you really want something unconditional for integers, I don't think we know anything for more variables. So with another master student, with Rocio, we prove this. In 4 variables, you look at the ABC equation in 4 variables, and you require the variables to be non-zero coprime integers. Coprime when you take the 4 of them, not pairwise, okay? And let me assume, sorry, I said this wrong. That was another one that's work in progress. In this case, you take pairwise coprime, okay? Pairwise coprime. And let me assume a condition similar to the condition I mentioned before, that one of these sums is somewhat smaller than the height of the 4 tuple, okay? Somehow smaller. In that case, you get a sub-exponential bound for the 4 terms ABC conjecture. However, this is obtained only using linear forms in logarithms, okay? And the question is, can you somehow mix this with the modular approach or the Shimura curve approach to get something improved or maybe to relax the condition on the size of the sums. Okay, so that's open. I don't know how to do that, and yeah. So here's the main corollary of this talk, that the influence of Professor Murty in the context of the ABC conjecture has been quite important, and I think this needs to be better known. And I guess one problem with this application is that not many people are working on the ABC conjecture. And I don't know why. I mean, it's true it's a difficult problem, but I don't think there are many people around trying to attack the question unconditionally. But if you are actually working on this, you will already know the first part of the corollary. And the second part of the corollary is that he was the best mentor I could possibly have. So thank you very much.
Thank you very much. Is there any question?
Just have a comment. Thank you very much for your effulgent praise, but I think you were a great student.
Thank you.
A student who works independently is an ideal student to have. I'm just wondering about, there are these variations of the ABC conjecture, like Moita has
Right.